Hey guys. So this week we are going to be talking about nonlinear regression models. Your book goes through a handful of nonlinear regression models. We're going to focus mostly on curvilinear relationships. We will get into regression models, logistic regression models, negative binomial models, and such later on. We're not going to talk about them right now. There are a lot of complexities that go into that. If you look at most of my research, actually, much of it uses nonlinear regression in one way or another. The two things that we're going to focus on today are curvilinear relationships and then data transformations. What do we mean by linear and nonlinear regression? We have a basic linear model, which is y equals a plus b times x, or bk times xk plus intercept. That is a basic linear algebra formula to calculate a slope. Curvilinear models, in contrast, add an additional slope to this model, and really it's a deviation from the linear slope. And so a curvilinear addition to a model suggests that what we've specified in a linear slope has one curve, either a curve up or a curve down. We can add a number of curves by squaring the variable. And indeed, what you actually do is you just simply square x, or you cube x, or you take x to the fourth power, and this is called curvilinear powers. Another approach is to look at logistic models in which you're trying to predict the likelihood of an outcome. So you want the probability, you want to know the probability that y is greater than 0 generally, and so the outcome is usually coded as zeros and ones, and you're trying to predict the likelihood of a 1. In this case, all of your slopes are technically exponentiated in order to get a ratio of for a given slope. We're not going to spend much time on logistic models, like I said. The book also talks about Poisson models. These are used primarily for count data. However, there's a whole slew of outcomes within the generalized linear model, which is an extension of the general linear model, that allows you to specify both count and non-count outcomes, as well as examine outcomes with zeros and control for or model when there are excessive zeros. The problem is, the book doesn't point this out, but the problem is with Poisson models, there's a very specific distribution that your outcome has to follow in order to specify it as Poisson. There's a density function that you can use if you specify it in a different form called a negative binomial, but right now you guys don't need to worry about that. And then a final thing that we'll talk about at the end of this video are transformed variables. And we're going to discuss why you might use a transformed variable for one reason or another, and when to transform your x variable versus your y variable. All right, so let's talk a little bit about polynomials and curvilinear relationships. As I had just said, the way that we look at these is simply by squaring x, and so we wind up creating a new variable in which x is squared or cubed or whatever. And so we start with a basic linear slope in our linear model. And this slope here would kind of represent what we've got right here. And then we would add to this a second piece, a quadratic piece, right? And in the quadratic piece, you are simply squaring x. And now you see this deviation from x. We can move to a cubic model as well. And in a cubic model, you see your basic linear model as well as the deviation, the bend up, and in this case there's a third bend down. And the bend down here looks pretty substantial, but I can tell you, and you'll see this in your homework or in class today, this week, that this bend actually is not statistically significant. It doesn't matter though. These are the three types of functions that you can look at with curvilinear relationships. Now theoretically, you can look at a whole host of functions. You could look at the fourth power, fifth power, sixth power. However, anytime you're doing these, they should be guided by some sort of theoretical rationale. And we're going to get to that a little bit later on in this video. Suffice it to say, though, the way that we look at these is by graphing them out. And in the final graph of this, what you're mostly concerned with is not this or this overlay or even this overlay, but what you would graph is this final piece here, right? And we'll talk about how we do that, and in fact, in class, we are going to go through and make that. So let's talk about orders, because in polynomial regression, you can see here we are gradually adding a squared x and a cubed x, right? And so we have what is called, oh, I'm sorry, I didn't do all that, higher and lower order terms. This is the higher order term. This is the basic term, your linear term. And in order to add the next step in the progression, you have to have all of your lower order terms included. So in order to even look at this one here, a squared x, you have to have a linear function of x in there. And so without it, this would make no sense. This regression equation would make no sense if it was just b squared times x squared. This is an important point to remember because this point is going to hold true when we get to looking at interactions as well. In interactions, you're going to have two higher order main effects followed by, or three depending on your interaction level, followed by a number of lower order interaction effects. And essentially, interaction effects are the same thing as a quadratic effect like what we're doing here, but it would be between x and m instead of x and x. Similarly, as we move on to the cubic model here, we have another lower order effect, and that means that in order to include a cubic effect, you have to have the quadratic effect and the main linear effect. So when it comes to detecting polynomials, what do? It's pretty easy. We start by doing this in steps, the same way that you did the steps for your homework this past week. You would regress x onto y, and you would have in step 1 a linear effect. In step 2, you could add a quadratic effect, and if you have a significant quadratic effect, you will have a significant slope for b2 right here, and a significant change in your f statistic and your r squared. You can report both of those things as a step 2 model, examining a quadratic effect, and then you would move on to step 3, and in step 3 you would add this cubic effect, and you would see if this slope is statistically significant, and if adding this effect results in a significant improvement in your model evidenced by a significant change in your f statistic or a significant change in r squared. Like I said, in this one, you actually wouldn't have that. So what you do is you add those things. It's theoretically possible that you would add a cubic effect and it would not be statistically significant. However, you would have a significant improvement in your model. Alternatively, you could add a cubic effect and have a significant effect but not have significant improvement in your model. At that point, theory guides whether or not you keep that effect or not. But enter and removal of polynomials tends to be based on a function of whether or not the model is improved and or there is a significant, statistically significant evidence of some sort of curvilinear relationship. The last thing that we do when it comes to detecting polynomials is we examine graphical displays. In the current, these current things, these are the graphical displays for quadratic, cubic, and linear. And if we did not have this quadratic effect here and we just had this linear effect and this cubic effect, we might look at this and say, actually, this does not really matter. Possibly, we look at the range of x and see that the range of x actually stops at 2.5. It doesn't continue on like this. and that quadratic effect winds up being very kind of on point with the linear effect. And if you have a large sample size, you might find that you have a significant quadratic effect, but in truth, it doesn't vary that much from your linear effect, and in which case you might decide, you know what, this effect is there, but the magnitude is so small that it's over explaining the model, and you would not use it. So examining your graphic displays of curvilinear relationships is extremely important, and we're going to spend a lot of time doing this in class this week. Finally, there's an issue with curvilinear relationships when it comes to examining centering. Now, this can be particularly problematic when you're talking about longitudinal data analysis, and we're not going to focus on longitudinal data analysis right now. We're just going to focus on simple cross-sectional bivariate analysis. So when you don't center, recall we talked about centering already, and centering is when you subtract the population mean from every observation. When you center a variable and then you multiply it times itself, you square it, you help to reduce non-essential multicollinearity. We have two different types of multicollinearity, and centering helps to reduce at least one of these. Essential multicollinearity is multicollinearity that occurs as a function of the fact that you are multiplying x times itself, right? And so there's going to be some overlap in doing so. Non-essential multicollinearity is a function of the fact that x is not going to be perfectly normally distributed. And if it were perfectly normally distributed, then there would be no non-essential multicollinearity. But since we have non-essential multicollinearity, centering this moves the distribution of the mean, and it allows you to partial out where we would have clumped data, and consequently clumped data times itself makes for an even more skewed distribution. Here's an example here. So we have an outcome variable, yak tote, and then we have the variable drinks, and you can notice that the correlation between number of drinks and alcohol problems, 0.65. We've centered drinks here, and again, it's 0.65. And then we have squared drinks here, okay, 0.65 or 0.64 with yak tote. And then we have squared the centered drinks here, and you can see that there's a dramatic reduction between drinks and yak tote, and that is because of this clustering. More important is this piece here. Notice that the correlation between drinks and squared drinks is 0.94. This really highlights the fact that we have non-essential multicollinearity in here. In contrast, the correlation between centered drinks and squared centered drinks is 0.2246. It removes non-essential multicollinearity by spreading out or reorganizing where zero is in here. The regression models that you do actually will be no different if you use this versus this, at least for this interaction effect, though these effects will change and your intercept will also change. For all practical purposes, you should always use centered variables when you are forming curvilinear relationships. All right, how do we interpret these things? So a quadratic effect means that you are going to get a slope that is either positive or negative, and that positive or negative tells you what is happening with the linear main effect. So, for example, if you have a positive linear main effect and a positive quadratic effect, that means that your line is starting to curve upward. In other words, this is a positive linear slope and a positive quadratic effect. Your line begins to curve upwards. Were it negative, were we to have a negative quadratic effect, then your line would start to curve downwards. That brings us to the next thing. Cubic effects actually talk about the next bend in your data. If you have three positives, then what you're talking about is a rate of change, a normal linear rate of change, an acceleration in that rate of change, and then a peak in that rate of change because it would continue to trend upwards. Here we didn't have that. Actually, we had positive, positive, and negative. And what that means is we see two bends, right? We see initial bend and then a new bend that starts to dip back down. So this is how we interpret those effects. Again, the easiest way to do this is to graph them, and then you can talk about the interpretation of those effects within the context of your paper. What order of polynomials do we test for? Like I said, you can test for any number of polynomial effects. In social sciences, the standard is to go no further than 3. And sometimes there's a question about whether or not testing for those is even appropriate. But the truth is, we expect curvilinear effects. In reality, almost nothing is truly linear. And so those curvilinear effects allow us to examine things out beyond what we would normally find, or examine things as they occur in nature, not out beyond, but as they occur in nature. And then again, we take, as I said earlier, a statistical significance / R-squared change approach, similar to what you did with homework this week, in which you looked at step 1, step 2, step 3, and you examined whether or not adding things to the model really improved the overall fit of your model. All right, moving on a little bit. Aside from polynomial effects, we have what are called nonlinear transformations. These include things such as square root transformations, logarithmic transformations, inverse transformations. And what we're talking about here is, there's a misconception right now. There's a misconception out there that if your variable is heavily skewed, that you can't use it in regression analysis. And that's not true. What we're really concerned with is the skew of the residuals, not the skew of the actual observation. However, if you have a normally distributed outcome variable and a heavily skewed predictor variable, you are almost guaranteed to get non-normal distribution of residuals. And so what that is, excuse me, if you recall from last class and last video, that is heteroskedasticity. You can address this by transforming either your x variable or transforming your y variable. You can do this using a natural log transformation, in which we will do this in class, or a square root transformation, or an inverse gamma transformation. And then you can look and see, if you do these sorts of transformations, does it bring your variable, your predictor or your outcome variable, back into what would be considered more normal? And does this result in a normal distribution, or at least a somewhat normalized distribution of residuals? The rationale for doing this has nothing to do, again, with the skew of the variable, with x or with y, but it has to do with the skew of the residuals. And what you're really trying to do is linearize the relationship between x and y, and you do so by engaging in some sort of transformation. There is no guarantee that it will linearize it, but it does. It provides you one kind of avenue to start approaching this. How do you decide whether you transform x or whether you transform y? Usually, the decision is based on which one of those variables is heavily skewed. However, I will say this. We are getting to the point where we have so many potential link functions and log functions that we can use to specify the outcome of y, that it's increasingly less common to try to transform y in some manner in order to bring it back into normality. It's not completely uncommon, but it's less common. One of the bigger issues is when you have negative and or non-zero outcomes, and then a heavily skewed data set, Because if you take a natural log or a square root or an inverse of a variable that has a lot of zeros, and just to throw this out there, if you have a lot of zeros, an inverse wouldn't matter anyway, because an inverse tackles kind of positive skew. I'm sorry, negative skew, while as natural log and square root tackle positive skew. But what you can do is you can add a simple constant, a very low constant, something that would put you just over 0. So for example, if you have zeros, you might add 0.01 to all of your outcomes if 0 is your lowest value, and that will allow for a true transformation of that data. If you try and transform zeros, you will get nothing. It's not a real number. Think about the square. What is the square root of 0? It's nothing. Okay, that is everything for today. I will see you guys this week in class.